So today we're going to be considering the problem of software security from a slightly different angle. Basically, what we have heard in the previous talk was more about like external intrusive into the either perimeter, but if software has a bug or hackers can break the logic of the program, it doesn't matter how well you protect your network, you can screw up. A little bit about myself. My name is Georgii. I've been writing code more than 10 years, maybe around 15 years every day. And what I really hate is fixing bugs. I don't like when people send me like, oh, this thing doesn't work, we need to fix it. And then you fix it and then reiterate and something different, you break something different, and this basically never ends. And I really hate it. But I think especially if you work in certain sensitive domains like finance, those bugs and mistakes can cost billions. And usually how we guarantee or how we test, verify software works as expected, well, we have the whole spectrum of different techniques with different capabilities and pros and cons. Like, of course, manual testing may be the first thing that comes in mind. So a person, like an end user, mimics behavior and tries to use the software in a way users will use, or try to break it. Unit testing is like some engineering purpose. Basically, it's about ensuring that functions work as expected. Integration testing is when different systems and components are tested how they work together and if everything is nice and good, smooth. End-to-end testing is very similar, but we run the whole user experience procedure to reproduce higher level behavior. And like fuzzing or property testing is when we use brute force to try to find certain combinations of parameters that make software works not as expected. And if we are lucky and stubborn enough, we can achieve something about 80% of coverage, barely. But it's pretty good, I think, especially for big systems, enterprise systems. Of course, the more specific the piece of software is, the higher this coverage can be. But, even with the 80% coverage, and if you're on the board of the aircraft, is it enough for you to be satisfied? I'm not sure. Yeah, might be. It depends on how risky you are. If we ask ourselves, what do tests check? And the answer is tests validates that some given function f with a certain input a produces the result b. And this is like a very straightforward approach. In another simple words, if a function, or if we consider a piece of software as a black box, that's reacts appropriately on our input. But what is the problem? What is fundamental problem that can break the system? Why system fails? Not only because functions are not implemented properly or have implementation bugs, but because of logical misconceptions. And where these logical misconceptions can come from? Well, in the old school software development lifecycle, what it looked like that. So a client somewhere published a list of requirements, what system they need, and the business analysis worked together with the client, then delegate information to project manager, and the project manager together software like architects or whatever all it is named with developers, and they produce a product. And this system worked well. However, all these testing techniques were invented before, right? And why? Because each right arrow here from party to party, actually this information transmission augments reality a little bit from party to party. It's like a game of telephone. And this is very behavioral thing for human beings, because different people can read the same sentence in a different way. It depends on on your mood, or coincidentally you choose one or another. And now the problem, I think, became even worse, because what's happening, people, they just break this chain and use AI as a shortcut. You just open Cloud Code, whatever you want, and like, hey, make me a authorization, implement authorization based on OpenAuth or other protocols, OpenSSL, and I will use it. No, of course you will not. You can, but most likely it's not gonna work. Instead of a game of telephone, you start playing Russian roulette. And because, sorry, like nobody take responsibility in this situation. AI doesn't have like emotional connection to the job. It doesn't afraid of losing job or anything. So it's like a very risky thing. What do we actually need? We actually need to ensure the code we have does what we want. Not only reacts on the certain input in a certain way, expected way, but like genuinely from the common sense perspective, it does what it should do. So that logically correct code is sound, like a mathematical sound system without internal contradictions or other problems. And formal verification is one of the most advanced techniques that allows to provide the highest possible guarantees about software correctness. And how many people here have heard or use everyday formal verification in their job? Nice, nice. What tools do you use? Do you want to share? Which one? Okay, what's other, maybe, who use Lean or Rock? Nice. Lean is very cool. Okay, then like crash course about what formal verification is. So we need to, on the basic level, we need to know two terms. One is theorem or proposition. It's like a type or type signature for developers. And proof roughly equals to a function where program, term, function, body. Okay, so only two things. Theorem is a type and proof is a function. Okay, crash course is done. So this is the very basic theorem. What is about? It says like if we add the 0 to a natural number, this natural number remains the same, meaning like n plus 0 equals n. And so this type of code is very, resilient, and it's very hard to break. This level of this compiler, this particular code is a piece from Rockproof Assistant. You cannot, convince that your code actually is implemented correctly. Here, is it like a scribbling or is readable? Or I need to explain more here? Okay, if I need to explain more, what's happening here, as I said, we try to prove that if we add 0 to a natural number, the natural number remains the same. We use induction here, meaning like we consider the base case and the common case. The base case n is 0, and if n is 0, then 0 plus 0 equals 0. It's a trivial statement. And if n is not 0 but any other natural number, we can, like in school, simplify this statement and using the fact that this should be n plus 0 now equals n, we can substitute and rewrite this expression with this hypothesis and achieve the desired proof completion. This basically what's underlying logic or foundation here is what's called reflexivity within here. I mean, we needed to be able to tell whether or not two parts on the left and right side of the equality sign are actually equals. And the process of reflexivity goes through the beta, delta, eta, and zeta reductions that basically granularly, step by step, reduce code. That's why they called reductions to the very similar expression that are at the very low level are not distinguishable and can be compared like strings, literally, actually. Yeah, and why it works? Because the calculus of inductive constructions theory works behind the scenes. So sometimes inductive is missed. So you can Google either calculus of inductive constructions or calculus of constructions. The QR code is there. So calculus of inductive constructions is a language, or it's like a meta language. It can be interpreted and implemented in either logical propositions or in code. And this interesting phenomenon makes it very usable for mathematics being represented in code. So term in our world is like term is everything basically. Constant, propositions, variables, everything. And this common umbrella term includes various sorts, like propositions and sets. Sets can be a number of subsets or variables, constants, or certain definitions, and what is called type I. Type I is a hierarchical structure of embedded into another universe, each of which contains a certain number of terms. And maybe this diagram I prepared is not super representative, but this QR code navigates you to the plain English explanation. So basically what we need to know that this hierarchy is well organized, and believe me, for many years, decades, smart people have been developing it. And the key question is, can we trust Rock interpreter compiler that what it does actually sound? There are no contradictions. And actually, yes. Because simply, as you remember, reductions, they reduce like very math-like code to the very literal strings. And by the theory, by definition of Curry-Horvath correspondence, which we already know because functions, the theorems are functions and proofs are function bodies, what we need to do with all that is to type check that types are matched, all constructors are covered in pattern matching, etc. Yeah, so this is a quote from the Software Foundation series. Very nice book, or 6 volumes, maybe 7 volumes so far. Highly recommend to read. It might sound very unintuitive or very complex actually, but there are some tools that allow to, not trying to assemble proofs and theorems from the ground up. For instance, I don't know if you can see it well. So here, the spec is very simple for the functions above. Check foo checks if x more than 1, and check bar returns checks if x more than 0. It's not the rocket science, right? And so this can be actually with the specification that checks that these two functions together produces the chain. If we have here an arbitrary x, then we can check foo and check bar. Therefore, x will be, as with this theorem, more than 1, right? Because we can literally skip, because if x more than 1, it's automatically more than 0, right? And the theorem for our spec is like we use binary numbers z. It's like n, but also includes negative numbers. And then we just collide everything to this expression which said like if x more than 1, percent z means like this type. It implies that x more than 0 as well. So this example shows that it's not necessary to write all the time very thorough math, because somebody did it already, and these tools help a lot. And if you ask who use formula verification, well, these guys do. For various reasons. Like here, I think it's clear that it's very undesirable. Aircrafts or spaceships, explode, or if AWS authorization has a bug and someone like from one enterprise can get access to another enterprise account, it's very, undesirable. Okay. Now, with formal verification, we have one thing that can really be helpful. We need some environment or virtual machine that we verify our programs onto, because it enables very interesting things. If we use a virtual machine and we assume that virtual machine implementation bug-free or strictly follows AVM specification, then it means that we can reason about the code behavior or execution on this virtual machine and be sure that our real execution will be exactly as we have in our theory or in mathematical model. So what is a mathematical model of a virtual machine? Well, it's called mechanization, and mechanization formally, meaning in mathematical terms, describes virtual machine as a finite state machine with the following in the following way. So any virtual machine can be defined as a memory, stack, etc., some small components, and which forms context and union with operations that can be executed on this virtual machine, so that the next state of the virtual machine is a delta reduction from the current state, operation, and the context. and delta, also known as a reduction from S to S prime. And mechanization in these terms actually ended up being a formal definition of delta, of reductions for, like a common reduction for all possible operations. So if we have two things, two components, like a virtual machine, well-defined, very nice, as WebAssembly is, and Rock, very mature proof of system, has been around for several decades and been used by big names, we can achieve very powerful setting. Why WebAssembly is good? Because the instruction set is relatively compact, because it's state-based virtual machine. It's portable, very little resources are required, and perfectly defined formally. This core code leads to WASM specification. And many companies use it, actually. I think in vehicles producers, these like dashboard displays, they sometimes use WASM to render the picture. And like it's everywhere because it's very nice. But we have problem here because no matter what environment we use, I think if it's like tries to pretend to be able to process any arbitrary computation, there are several caveats. Number one, and of course WASM is not exception. So floating point computations is something that leads to non-determinism, right? Because I754 standard, there is no particular like strict rule how a hardware works with not a number. Therefore, we any implementation that satisfies basic rules can be is acceptable, and host function calls are not under our control. So for WebAssembly, host functions are functions of a web browser or another environment WebAssembly is run on. Yeah, non-determinism is not the same as undefined behavior. Non-determinism is actually a enumerable set of all possible legal states or operations a program or software can perform or do, whereas undefined behavior is something illegal, like reading from unimplemented memory in low-level languages. So here, non-determinism, it can be, we have a variety, and any case in this, like item in this variety of all possible cases are okay. Undefined behavior is something like it's broken. So this is how we tackle floating point, not a number case with WebAssembly. So the definition is, so what we want to answer here, so this is proposition. Proposition is not a computational unit, it's not a function, it's more like a predicate for a function or for some other computation. So the job of a predicate is to give an answer like true or false, basically. And here we compare if like two results, computed and actual results, compatible. And such results are compatible either if they're equals according to the Leibniz equality statement, which means that two values are equals if they're constructed identically, and this is recursive statement should apply to any constructor and subtypes in which can be part of a type. And if they are not, then we have here like an alternative branch with the match and pattern matching. So two floating point numbers have the same not number. They're compatible if both of them are not a number and both of them are canonical numbers. Canonical not numbers. Sorry. Yeah. Crash course about the canonical, non-canonical floating not numbers for floating point standard IE754 is that in Mantissa the first bit actually named as a quiet bit shows whether or not the Mantissa is number, not a number, and the why I said it's non-deterministic because here. Standard says only about the first bit, and there's like canonical, not a number, says that it should be like a first bit and then all zeros. However, arithmetical, not a number, can have first bit, but the rest memory can be dirty. So I mean, it's kind of work for arithmetics because it can be like CPU optimization. You don't need to clear the memory here in Mantis, and you just flip one bit, and here you go. But in Rock or in Proof Assistant, we cannot kind of deal with this. We need very like bitwise comparison all the time. And to be able to work with floating point numbers, we have this proposition that actually helps us to to process and to satisfy a type checker with arithmetical not numbers. Yeah, this is so because we have here implication. Yeah, because A is a if we imply that here that A is canonical, which is a more strict, strictly required thing, then we need to. It's okay for us to assume that the premise is also at least canonical because it has more relaxed. Come on. Okay. One second. Yeah. Okay.
This should be okay.
I'm not sure if I need to explain how to use this. I can really briefly. So basically, why we need it, as I said, because as a virtual machine, you might know, like virtual machine, right? It runs on some physical machine, on the host system that actually, and instructions that virtual machine emits, they're being propagated to the actual hardware, like CPU, to execute. And therefore, we should, if we follow only one standard, then it breaks our portability to any platform. Therefore, we need to convince a type checker that we can deal with. And we use this predicate as non-compatibility number after the execution with the result. So like we check if whether canonical or arithmetical mantis is presented, and then we can go along. It sounds complex, and you might ask, like, okay, I can use Cloud Code or whatever. Like, there are many solutions out there being built to, deal with formal verification because, there is, marketing is very aggressively tell us that it's possible. However, the problem of this approach is that imagine you have like 5, 10, 20,000 lines of math code, and if somewhere vendor writes something like false implies true, then it, this axiom somewhere burden in a very deep level, well, it means that all your theory is unsound, because if you can, from false, you can imply true, that it means that you can prove anything. Okay, so the final thought is mechanizations. Virtual machines are good because it allows to use formal verification effectively with very clear boundaries, and like cryptography algorithms that are implemented in for these particular environments are very highly reliable, and many other cases, whatever you can imagine. If you want to learn more, there are several links here. For example, this Software Foundation series of books is like a university course curriculum for quite extensive time. Yeah, we recommend to read. Any other links? And thank you. This is the last slide.
Okay, thank you. Yes, it's a very complex topic. So, any questions?
Yeah. Nice. Yeah.
Thanks. I have a few questions, and they're all about AI.
Okay.
So the first question: if we talk about AI as an LLM system, does it have a deterministic result or undefined behavior?
Okay. I don't think it. Okay. Undefined behavior, for my how I see it, it is a very low-level stuff, which are like very unlikely to happen with AI. You mean AI as a model, right?
For example, an agent system.
Agent system. I think non-determinism is more applicable here, because if it's an agent system, it should be like very, like on a low level, on a protocol or on a network level. High-level concepts, they're usually, I think, well, for me, it's a little bit hard to imagine more of non-determinism. And non-determinism is actually the very essential of AI models, because the temperature that you change actually impacts on the how less deterministic the model is. Simply sitting like with the more or less randomness, sit in the initial prompt, and even with this, even if you use like temperature 1, it does not mean it will be deterministic. Simply because when you multiply several multidimensional metrics with the precision of 16, like for example, right? Then what happens is during this computation, massive computation, the rounding error tends to be accumulated during the time, and it means that every next computation can accumulate an error, and you don't know how what is the next vector multiplication. What direction it goes to. It can be very, the non-determinism is a very basic property of models, AI models.
So is it possible to use formal verification to test those non-deterministic agent systems?
I haven't heard about this, simply because, to apply formal specific verification, you need what is called formal specification. It means that you need to formally define the behavior of a model. And since it's behavioral, non-deterministic by nature, you simply cannot. If you could, it would mean that if you your input prompt is A, it always returns B, but it's not the case. But what's happening now, the opposite thing. So people use LLMs to generate code for proof assistance. Yeah, but not vice versa. like it's a fundamental problem. Yeah.
Okay, thank you very much.
Yeah, thank you. Yeah, I think we have Mike.
So any question? Yeah, sure.
Yeah, thank you very much. Can you hear me?
Yes.
It's very fascinating. And
Thank you.
yeah, I was thinking. I think for instance, before there was that you were talking about, it's the finite the state machine. But I thought the WASM is more like the finite or non-deterministic automaton. So in that sense, I think what level of the computational model you are focusing on with this verification? That's my first question.
Okay, so how we consider the finite state machine or automata? I can draw various like deep, I think, example. Maybe it can help with the intuition. So as I wrote this, we need a context, right? So this is where our current state, current state is, right? And we have an operations, and this state is a context of memory, right? And it means that the number of transformations and ways to go to switch equals to the number of operations being applied in the context. And what it means, basically, we need to do pattern matching here, some kind of, right? And to write a very, very long pattern matching, considering all operations, which we, for each operation, here we apply in the context. This is the very kind of low level. And as it was said earlier a little bit here, because we, in fact, where is that? It's type checking, right? And we can see here it's nothing but type checking. So for any machine, we need to know all possible transformations for every state. And yeah, it's like it finite, right? Because we have trap in WASM, for example. Trap means like hard stop, like electricity off. And we have unreachable. So, I mean, this graph has exits always. Yeah, I don't know if it's answers on your question. Why is that? Simply because if we are thinking about an arbitrary visual machine, it should satisfy Turing completeness, right?
Yeah, it should be completeness, and then it should be actually deterministic.
Yes. Otherwise, so if it's not, yeah.
Yeah, and the interesting issue is that of course, the gentleman talking about LLM, and then LLM is actually a transformer. Let's say focus on transformer.
Yeah.
Transformer is I would say it's a Turing machine, because you can do because that is the at least the two-layer the deep learning stuff. So you can prove it that that is. So but in that sense, and then also it is actually gives you that's Turing machine, but the input, the prompt input, and then output is actually it's a stochastic.
Yes.
Right.
Yes.
So in that sense, it's coming from the stochastic stuff. Probably that gentleman is talking about how we prove it. It's okay or not.
Yeah. So our question is, if we imagine a Turing machine, right? So Turing machine is actually is kind of an automata, right?
Yeah, automata.
Which
yeah.
Here's like operation 1 and operation n. And this and you have a memory. Exactly. This is the same thing actually. So in terms of Turing machine. And our next step is actually we take one operation, transforms memory. Okay, this is our state. And because of Hall's theorem, actually. We cannot, it's impossible to prove that the arbitrary algorithm is finite, halts on the Turing completeness, right? Because
Yeah, you can combine
loops,
it.
like you can
Yeah.
you can do whatever you want, right? That's why it's Turing complete.
Yeah.
So here, how I answered on the question about models, I was thinking about like if we project like it's like many dimensional matrices, right? And what we do, we multiply matrices all the time. And because these matrices are represented as floating point numbers, right? Like fundamentally, the higher the arity is, and the higher our precision is, I think the probability of rounding errors grows to some, well correlated. Like somewhere here on the 9th position, something can happen. But because of number of these multiplications, this rounding error can grow, and it makes like either we need to enumerate all possible states, which is impossible practically, right? Because of because you need to consider in this case 64 bits power number of parameters in this computation, which is practically impossible, right? So we need to somehow find a good boundary for what we can reason about. In our case, what we use Turing machine, which has exits like trap and unreachable, and of course, I mean it's like what EVM did. We track operations.
So that means basically you are putting some of the the condition of the stop.
Yes,
Okay.
it's like gas or fuel or well, we need somehow in order to overcome halt theorem, we need to provide some number which we can track. We can reduce to track how many steps we did. So it's called a structural recursion, for example. So in order not to fall into infinite recursion, it's algorithm or principle of structural recursions is used is when if you do a recursion call, and inside you call f, right? So you need to have some parameter like n here, which you must explicitly reduce inside the function call in order to be able to continue. So it's like kind of guardrail for recursion. And this guardrail is used in blockchain, so people do not explode it with infinite loops. Yeah.
Yeah, okay, thank you very much.
Thank you.
Cool.
We don't have any more time for questions.
Sorry.
This will be the last question.
Thank you very much.
Yeah, thank you.
Thank you.
Yeah, so once again, thank you to Georgii.
Thank you.